Okay, so Assalamu alaikum wa rahmatullahi wa barakatuh. Today we are going to continue the problem of an isolated foundation that we have started last class, in which we have stopped in bending moment calculation. First of all, my voice and the screen, are they clear?
Yes, sir, clear.
Yes, sir.
Okay, okay. So not to waste any further time, we will go directly to the to wherever we have stopped, where we have stopped at the calculation of the moment. When we said the moment due to the concept of being like a cantilever, since it's calculated from the face of the column till the edge of the foundation, it is considered to be a cantilever where your moment is WL square over 2. W is the pressure, L is the length from the face of the column till the edge of the foundation. In case if you are having similar length, then you will be having one moment. If there are different lengths, then different moments will be there. Now after the calculation of moment, further steps of calculation of reinforcement will be there, which are exactly similar to whatever you have done in the design of slabs. So we will go and calculate for K, okay, and then you can see here wherever there is D, we have used D average, okay. Wherever we have used D, it is going to be D average, and I'm going to explain why when it comes to two-way shear, why we have used D average, not dx and dy. Okay. So once again, after calculation of moment, there will be the calculations required to get the area of reinforcement, in which we said we need to calculate K, we need to calculate Z, and then we will be able to calculate AS. Okay. So this is a typical step, okay, or typical steps that needs to be done in order to get your AS. So after your K, you will go for your Z, exactly similar to whatever you have done in slabs. So we have Z1, we have Z2, and once again, whenever we are using D in the foundation, we are using D average. Okay, and you can see from both lever arms, from both Z and Z1 and Z2, we are taking the smallest of the two. And in this scenario, the smallest is Z2. After that, we are going to calculate AS, where AS is equal to M divided by 0.95 into Fy into Z. Fy has been given in the problem to be 460. M has been calculated already. Z we already know. So we have got our value of AS required to be 919. Okay, AS required is 919. AS minimum as well is going to be 0.13% B into D capital, since foundations are designed something similar to slabs as well, where B is 1000. We have assumed from the beginning that our width is going to be 1000, something similar to the slabs. Depth has been assumed from the beginning to be 550. So now we have our AS required to be 919, AS minimum to be 715. From these two, we are going to take the highest. Okay, my required area is more than the minimum, so we are adopting. Okay, we are adopting the required value. Now, after we get the required value, we will go and get the provided value. Either you use the equation which I have told you in the slabs design, that we are going to use the area of one bar multiplied by 1000, which is the width, divided by the spacing. So we will start the spacing by 300. If this area that I have calculated is not sufficient, I'll go for 250. Not sufficient, I'll reduce the spacing each and every time till I reach to a value which is more than the required. That's if you want to use this particular methodology. The other methodology is to use the table. The table is in front of you. You can go to the table. Okay. We can go to the tables in the extract. Okay. Size and area of reinforcement of bars. You can see slabs and foundations. And both of them, it is clearly mentioned that these cross-sectional areas per meter width. So when we talk about slabs and foundations, they are designed for 1 meter width. So you shouldn't come and ask me later what's the value of B. Both of them have been designed for 1 meter width, which is 1000 mm. Okay. So now you can see if we are choosing 20 mm, if we are using 20 mm, and then 300 is the spacing, I have my area of reinforcement to be 1050. Okay. Now 1050, and here we have got it to be 1048. Both of the answers are okay. Okay. So either you use the first methodology, which is the area, or you use the table. Are we fine with that?
Excuse me, Mr. Can
Yes,
you
sir.
repeat, please?
I cannot hear you.
I said, can you repeat, please?
Repeat what exactly?
The final part.
Which final part? The area of reinforcement?
Yes.
Okay. Once again, the area of reinforcement, whatever I have talked about, is not something new. That's something which we have done already in the slabs design. Okay, we said in the slab design, to calculate your provided area, you have two methodologies. One method is to use the table. Okay, the other method is to use the area of one bar multiplied by the number of bars. And we said the number of bars is calculated as the width, which is 1000, divided by the spacing. So first I'll assume a spacing of 300. Whatever value I'll get here, if it's more than the required, then it's going to be sufficient. If it's not more than the required, then it will not fit. I need to reduce the spacing. So rather than 300, I'm going to use 250. If the value is more than the required, then my spacing is going to be 250. Not, I'm going to reduce. If it's not, I'm going to reduce further the spacing, and it goes on. Okay. And once again, clearly you can see here that if we are having 20 mm diameter, which is the diameter that we have assumed, and we are using a spacing of 300, then we are having an area of reinforcement which is equal to 1050. Okay, which is equal to 1050, and in this scenario, our area of reinforcement required is 919. Okay, so the closest value to 919 is going to be 1050 for the diameter of 20. Now, if, for example, this area of reinforcement which is required was 1100, then 1050 or 1050 is not sufficient. We need to go for 1260, and it goes on. Okay, so either you use the table or you use the area of bars. Okay, calculation of area of bars manually. Are we okay now? Are we fine?
Yes, sir. Thanks.
Okay. Now, other than this, if you remember in the previous class, we have found the value of L. Since our foundation is square, we have found the value of L in both directions is the same. Okay, so if I calculate it for the right side or the left side, then my value of L was appearing to be 1.3. If your pressure is the same, your length is the same, then your moment for both directions is going to be the same. Okay, my moment for both directions is going to be the same, which will give you the same area of reinforcement for both directions. That's why here I didn't go and calculate twice, because both of the moments are the same, which will give me exactly the same calculation. So what I have done, I calculated one area of reinforcement. I said this area of reinforcement is to be provided in both sides. Okay, in the side of short and in the side of long, for the foundation itself, whether it's a square or whether it's a rectangular foundation. Are we fine till now? And once again, till now, whatever we have discussed is exactly whatever is there in the slabs. Nothing new. Are we okay with it?
Yes.
Yes.
Okay. Okay, so after we finished area of reinforcement and we have calculated the area provided, the next step would be to check for one-way and two-way shear. And if you remember in the last class, we have discussed when to calculate one-way shear and when to calculate two-way shear. Okay. So for example, in case of one-way shear, we have learned that we need to take a distance of D. Okay, we need to take a distance of D. Did I explain for you the one-way and two-way shear? I have explained this, right? One-way and two-way shear. Okay, so if you remember from the previous classes, we have said that in one-way shear is going to be acting after a distance of D from one side. Okay, so I need to calculate this particular portion. Now to keep it a bit clearer for you, okay, to keep it clearer little bit for you, this is my foundation. Okay, we said whenever the loading of the column is going to come, it will distribute in this manner of 45 degrees. Okay, now you will see that this particular loading is going down while the pressure is trying to stay in its position or pushing up. Now this particular location would be very hard to be elevated up, to be taken up. Why? Because there is a lot of concentration of downward force and upward force. Okay, so this particular location is very hard to be cut. Okay, which part is easy to be cut? It is going to be this portion, which is after a distance of D according to the code. Okay, or this distance. Okay, so now you will see we have this area which will be elevated up, or this area which will be elevated up. Now the good thing when it comes to square, this particular length of A and the length of B are exactly the same. So whether you take A or whether you take B, it is going to be the same thing for you. Okay. Now you will see that this portion is going to go up. It is going to be pushed up from its position, and this is going to go down. Okay. Now this is in case of a section. What about a plan? So this is my plan. And this is my square column. We said we need to have a distance of D. Okay. After this particular distance of D, this is the area which can be taken up, which is in this scenario B, or in the other scenario it is going to be A. Now the first thing that we need to do, can you tell me how much is the length of A and B? Can you tell me how much is this length? If we are knowing that this particular dimension of the foundation is 3 meter and the other dimension is 3 meter, and you know that the cross section of the column is 0.4 meter. Can you help me here in finding the value of length? How much would it be? How much is the length of A and the length of B? Okay, so you will see if we, for example, if we want to calculate A, okay, if we want to calculate A, then I have two methodologies or two techniques. One technique is to cut the foundation into half. So the distance from here to here is 1.5 meter. So I have 1.5 meter. I need to remove half of the column first. So minus half of the column, which is 0.4 divided by 2. And then I need to remove as well. I need to remove my D. So which is going to be the D average. We have got it, I think, in the previous calculation to be 0.48. Okay. So now if we go and calculate, these, we'll find that 1.5 minus 0.2, which is 0.4 divided by 2, minus 0.48. So that is going to give you A value equals to 0.8 meter. Okay. So this is methodology number 1. Okay. This is methodology number 1. Okay. Methodology number 2. Okay. Methodology number 2 is to calculate this particular location. Okay, so for example, A, let me use another color. A is equal to B is equal to 3 meter, which is the whole thing from here to here. Okay, minus 0.4, which is for the column, minus the first D minus the second D. Okay, which is going to be 0.48 minus 0.48 divided by 2, because there are two regions. There is one region here and there is another region here. Okay, so now if we go and see this calculation, it is 3 minus 0.4 minus 0.48 minus 0.48 divided by 2, which will give you 0.82. Are we clear about this calculation? Are we clear about this calculation?
Yes.
Are we fine about it? Okay, so you can use whatever methodology you want. Okay, there are other methodologies as well. The only thing for me, I need to see the value of A and the value of B. Now, once again, since this is a square foundation and a square column, your value of A and your value of B are the same. Okay. Now, when it comes to a rectangular foundation, your value of A and your value of B are not going to be the same. Okay. If for example, if your column is not acting at the center, so different scenarios are there. Okay. We will try to see these scenarios in the upcoming classes. Okay, the most important thing that you need to understand the concept right now. Okay. Now, if I want to take this particular portion, up like here, how much force is required? How much force is required to take this particular portion, which is B, from this particular location to be cut in shear? How much is the force required? Now the first thing, which force will take you up? Which force will take you up? What is the force which will take you up?
Pressure.
The pressure. Okay. So the first thing, I need to know how much is the pressure. And if you remember, the pressure we have calculated is 216.67 kilonewton per meter square. So you are telling me for this particular portion, which is B, which is having a dimension of 0.82 as a width and 3 meter in length, okay, it is having a pressure which is acting as an area load of 216.67 kilonewton per meter square. Right. Now for us, in order for us to calculate or to check for shear, we require to calculate shear stress, in which shear stress is equal to shear force divided by area. Okay, shear stress is equal to shear force divided by an area. So for me, I need to calculate the force, which is shear force. What is the unit of shear force? What is the unit of shear force? The unit of shear force, kilonewton. Okay, the unit of shear force is kilonewton. Now that's why I told you I need to know what is the force which will take my portion up. Okay, I need to know the force which will take my portion up. Now you can see that particular force is acting, the pressure is acting in an area form, which is 216.67 kilonewton per meter square. Now how to convert from 216.67 kilonewton per meter square to kilonewton? What are the things required for you? So V, which is shear force, would equal to what? Would equal to pressure, which is in kilonewton per meter square. Now what is the area which is affected? What is the area which is affected by this? Which area is going to be taken up? Which portion will be taken up? So I can say here that this is going to be the area which is affected. Now since it's an area, it is going to be in meter square. Now you can see I have a loading of 216.67 kilonewton per meter square, which will affect my area that will be taken up, which is 0.82 into 3 meters. And if I multiply these, okay, I'm going to get a value of 533.008 kilonewton. Now, is it clear whatever I have tried to do? Is it clear whatever I have tried to do? I tried to see what is the portion which will try to be taken up. Now, in order for me to know how much is the force required for this particular portion to be taken up, first I need to know the portion. And we knew that there are two portions, either A or B. Okay, either A and B or B. And we have found in this scenario, A and B are the same. Okay, so I have taken one of them. I checked the value of, I checked the portion which is B, and I have found that it has a width of 0.82, okay, and it has a length of 3 meters. That's the portion which needs to be taken up. Now I need to know what are the forces which will cause this particular portion to be taken up. And I can see that the force which will take them up is going to be your pressure. In which the pressure is acting as an area load. It is a load which is acting on an area, okay, which is 216.67 kilonewton per meter square. For each 1 meter square, my loading is going to be 216.67. Now for me, I need to calculate the shear force, okay, in kilonewton. So I need to know the total area of that particular portion, which is B, in which your area is going to be 0.82 into 3 meter, okay? And then I need to multiply it by the pressure, in which I'm going to have a final point load. So this is the point load required to take my portion up, okay? Are we clear about this particular V value for one-way shear? Okay. Now what about let's go for two-way shear. Okay, let us go for two-way shear. Before going and completing one-way shear calculation, let us take two-way as well. Now for two-way, we said it's called two-way because shear is going to happen in both directions. Okay, and we have discussed this in the last class. We said if we have a foundation and we have a square column, then we take 1.5D from each side. So 1.5D, 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 and then 1.5D. Do you remember this? Okay. Now we have two areas. Okay, we have two areas. Well, let's say three areas. Let us say three areas. This is 3 meters to 3 meters. I have one area, which is the full area. Okay, which is 3 meters into 3 meters. And I have the area which is inside. Okay, where this is going to be 0.4, this is going to be 1.5D, and this is going to be 1.5D as well. Okay, so 1.5D from here, 1.5D from here, and then 0.4 from here. The other side as well, we have it as 0.4. This is 1.5D, and this is 1.5D. So we can call this one to be total area. This is inner area. Okay, and there is another area. Okay, there is another area which is this area. And let us call it as an outer area. Okay, let us call it as outer area. Okay, let us call it as an outer area. Now, can you tell me which of these areas are supposed to be going up? Or let us start. Which one is supposed to be going down? Is it the inner area or the outer area? Or the whole area? Which area is going to be affected by the column mainly, which will try to go
Inner.
up in the case, okay, in the case of the pen, if you remember the pen and the paper. Okay, so which area is going to go down?
Inner.
Inner area. So inner area is going to go down. What is the area which will stay in its position or it will go up? Now see once again, if you are having the paper, You are pushing the pen inside. You will see that the pen is going to go inside, and then the paper a little bit will go up because of the force that you are trying to push. Okay, so which one is going to go up? The outer is going to go
Outer.
up. Okay, so the outer is going to go up, inner is going to go down. Okay, now what we need to do, we need to calculate in the same scenario, whatever we have done for one-way shear, we need to calculate how much force is required to take that particular portion up. Now, which portion is going to go up? It is the outer portion. Now, can we calculate? We have learned that V is equal to the pressure, which is in kilonewton per meter square, multiplied by your area. Now, which area of these two is going to go up? We said it is the outer area. Now, can you help me here in calculating the outer area? Can you help me here in calculation of the outer area? Pressure will not change. It is 216.67. How to find it? Can I say the area? Can you mute yourself, please? Can I say the area is 3 square, which is the whole foundation? Can you mute yourself, please? Everyone, can you mute yourself? Okay. What is this area? What is this inner area? Can you help me in calculating it? How much is the inner area? You can see that the inner area is equal to 3D plus 0.4 in this direction and 3D plus 0.4 in the other direction. 1.5D plus 1.5D is 3D. 0.4 is 0.4, so it's 3D plus 0.4. Okay. So we can say now it is going to be 1.5 or 3D directly. Let us take it 3D multiplied by 0.48. That's the D average. Okay, so it is 1.44 plus 0.4. So it is 1.84 for each direction. Okay, since it's a square, I can say that it is going to be 1.84 square. Okay, so now my outer area is going to be the total area minus the inner area. Okay, in which we can get, let us see. So this is going to be 216.67 multiplied by 9 minus 3.3856, which will give you so I have got this value to be 1216.47. Are you with me?
Yes.
Okay. So we have calculated the areas. We have calculated, the forces required to take the case of one way and the case of two way. Okay. Now we need to return to the concept of shear. Okay. In order for us to check for shear, we used to check for shear stresses. and shear stresses are measured. Okay, shear stresses, which is a small v, if you remember in slabs. Okay, we used to compare between V and VC, where V is for the load and VC is for concrete. Okay, which is load and then concrete. Now we used to calculate V, which is equal to shear force, okay, minus shear area, the area which will be affected by shear. Okay, this is my V smooth. Now we have managed to calculate the shear force for both scenarios. Remaining is the shear area. And to keep it simple, I'll just call it as cut area. It is the area that I need to cut. Okay, it is the area that I need to cut. Now, if I go here, if I go for the case of one way, assuming that this particular portion or this particular foundation is acting as a cake now. Okay, it is acting as a cake, and I have a knife with me, and I need to remove this, which is B. Okay, I need to remove this portion, which is B. Okay, once again, assuming that the foundation is acting as a cake now, I have my knife as a cutting tool, and I want to remove this particular portion of B out. So it is going to be out. What are the things needs to be cut? Which dimensions you need to cut? Remember that this is 3 meters. This is 0.84. This is 3 meters as well. What are the dimensions that you need to cut using your knife? Now, for example, if I brought my knife and I started cutting from here, I went to here, will part B go out? Will the portion of B, will it go out if I reach only to this point?
No.
Okay. What about here? What about here? Will it go up? No. It will only go out if I cut the full length, right? It will go out only if I cut the full length. Do you agree?
Yes.
Okay. Okay. So one dimension that needs to be taken into account while cutting the portion is going to be your length. The other thing to be taken into account, now if I have, for example, this is my plan, and this is my depth. I mean, this is my section, and I want to remove this particular portion. I want to remove it up, or I want to take it up. Okay. Is it sufficient for me that the knife will enter to here only? Is it sufficient that the knife will only cut that particular depth amount? Will it go out even if you cut for the full length? We agreed that we are going to cut for the full length. Now, if the knife only cuts a certain depth, will B go out? Will it go out? No. Okay. You will see, if I want to remove B portion, I need to cut for the whole length, and I need to cut for the whole depth. Otherwise, this particular portion of the cake will not go out. Right? Okay. So which dimensions that you have cut? Which dimensions that you cut? You will see the area that you have cut. The area that you have cut is representing, okay, the area that you have cut is representing a dimension of L and a depth of D. This is the amount, or this is the area that my knife is going to cut. Do you agree? My knife is going to go through this plane only, which is the plane of length into depth. Do you agree? Okay. Now, can I say if I'm calculating for my V small, which is going to equal to shear force divided by shear area, I can say that my V, which is shear force here, is going to be 533.0082 into 10 to the power of 3, since it's kilonewton. And stresses are normally measured in Newton per millimeter square. Area, what is the area that I have cut? Or what is my cut area? My cut area is representing L and D. My L is 3000 or 3 meter. My depth is going to be 0.48. Now, can you give me this value? Can you give me this value? Can you give me this value of V for one way?
37.
How much?
37.
Sorry, this shouldn't be 48.48, because 3000 in millimeters, this should be 480. Okay, since we are having the unit of stress in Newton per millimeter square. Okay, it should be, all the units should be in millimeters. So if it's 3 meters, then 3000. If it's 0.48, then it should be 480. How much is it going to be? Do not forget that there is 10 to the power of 3 here. The final answer should be going as 0.37. Okay, the final answer should go as 0.37. Okay, the final answer is 0.37. Okay. This is a calculator. So 533.0082 multiplied by 1000, which is 10 to the power of 3, divided by 3000, divided by 480. Then my answer is going to be 0.37. Okay. So we have calculated the shear stress for the first scenario, which is one way. Now going for the second scenario here. Going for the second scenario. Now already we know our shear force for two-way. Now the remaining is the cut area. Okay, the remaining is the cut area. Now can you tell me, if I have a cake, once again, if I have a cake and I want to remove I want to remove this portion, this brown portion, I want it to be taken out, okay, which will be in this scenario, okay. Okay. What are the portions that I need to cut? What are the portions that I need to cut? Now, if I brought my knife once again, if I cut this dimension, will I get this shape? If I brought my knife and I only cut that particular dimension, will I be able to get this shape? No. Okay. If I cut the second one as well, will it go out? Now remember, I can have this shape by removing the inner by removing the inner area. I can remove the inner portion of that cake and I have the outer portion. So it is not sufficient to cut 2 dimension. Is it sufficient to cut 3? Will it go out? No. What about 4 now? Will it go out? Okay. Now, if you imagine with the cake, you will see that by cutting the 4 dimensions, it is possible for me to remove that area. So I have how many areas or how many dimensions to cut? I have D1, which is dimension number 1, dimension number 2, dimension number 3, and then dimension number 4. Now, is it important that I cut the full depth, or I can cut only, a certain portion of the depth? This is my foundation. And this portion needs to be taken down or taken up. Is it sufficient for me to cut for this amount of depth as well here? Here I need to take both. So do not forget the other side as well. Is it sufficient for me to cut these amounts? Will it go? Will the inner area go down and then I can remove the outer area? Or I need to cut for the full depth? Full depth. Okay. So now what you can see that I need to cut my knife needs to cut dimension number 1 with the full D average, okay, and then I need to cut the other dimension with the full depth of D average, and then as well I need to cut the other 2 dimensions, okay, the other 2 dimensions which are available here and available here, okay. So now you can see that you will be having 4 areas. Okay. You will be having 4 areas. So I can say now my cut area is equal to D1 into D average plus second area D2 into D average plus D3 into D average plus D4 into D average, which can be written as B1 plus D2 plus D3 plus D4 into D average, which can be written as perimeter into D average. What is the meaning of perimeter? Perimeter. What is the meaning of perimeter? Perimeter is another name for circumference, اللي هي المحيط. Okay, so I have 1, 2, 3, and then 4. These are this is the circumference of this area, okay, or whatever we call it as perimeter. So mine is going to be P into D average. Now, here you will know why we have used D average, because you have direction of X with a combination of direction of Y. So I cannot use X separately here, or I can use the direction of Y separately here. Okay, it's a combination of X direction and Y direction. Okay, that's why we use D average. Okay, now going to this particular equation, we can see that V for two-way is equal to my shear force. How much we have got our shear force? We have got it as 1216.47 to 10 to the power of 3. Okay, to convert from kilonewton to newton. And then we have the perimeter. Perimeter اللي هو circumference or المحيط. Since it's a square, then it's going to be 4 times. Since it's a square, it is going to be 4 times of this length. What is that length? We have got the length to be 1.84. Okay, so I can say that it is 4 times of 1840 multiplied by my D average here, which is going to be 480. Okay. So now you can see 1216.47 into 10 to the power of, or multiplied by 1000 directly, divided by 4 times 840 divided by 480. Are we getting it to be 0.344? Okay. So what I understood now, I understood that the amount of shear stress which will be caused by the pressure, by the upward force of the pressure, is going to give me 2 scenarios. Scenario number 1, if it's one way, and we have got it to be 0.37, and two way, which is 0.344. Now I need to check how much the concrete can take. Now, if you remember, once again, we used to compare between V and VC. V is the amount of shear caused by the load. Now, for one-way and two-way shear, it is caused by the pressure. I need to know whether these particular shear stresses are stronger than the capacity of the concrete. If they are stronger than the concrete, then they will cut the concrete. To avoid that, we need to get a solution. Okay. Now, before deciding whether they will cut the concrete or not, we are going to calculate for the value of VC. Okay. But first, before going to VC, is everything that I have explained for you here clear? Is everything that I have explained for you here clear? Okay. So returning to the presentation, you can see now that this is an illustration. This is an illustration of whatever I have explained for you. This is in case of a one-way shear. So you can see that that particular length is 0.82 in one direction. In the other direction that we need to take into account is 0.48 as well. Now, why I didn't do this because I have a square column and a square foundation. So all the dimensions are going to be the same. No need for me to go and recalculate the other direction as well. Okay, all of them are going to give you 0.82. Okay, the one-way shear, we have it as shear force divided by shear area. We said shear force is equal to the pressure, which is the loading, which will take you up, multiplied by the area of the portion to be taken up, which is area affected. Okay, and we have got the area affected, which is colored in red now, is going to be 3 into 0.82. I'm going to multiply it by the pressure. I have got the amount of force required to take this particular portion up. Now, after I know the force, I need to know which area or which, let's say, which panel will be cut. Now, in that scenario, to make it easier for you, I have explained for you or I have given you the example of the cake and the knife. Can you see? Now you can see if I want to cut, I will cut the length of 3 meters. My knife should go for the length of 3 meters and a depth of 0.48. Okay, so my cut area is 3000 into 480. 3000 is 3 meters, 480 is 0.48. But these are in millimeter now. Here I have got my shear stress as this amount, okay, which is 0.37. The same thing goes for two-way. Okay. So we have 1.5D. So 1.5D is 0.72. Okay, so we have calculated all the sides and we have come up with inner and outer area. Okay, inner and outer area. And now we need to calculate this particular blue color. This particular blue color is the portion which will go up. And we need to know how much force is required to take this particular portion up. In order for me to know how much force, I need to convert from kilonewton per meter square pressure into a point load, okay, in which we have done pressure into area affected, which is the area in blue, which has been calculated as 3 square minus 1.84 square, because it's a square column and it's square foundation. If it's not the scenario, then you will not be getting it in this way. Okay, you need to calculate the area. If it's rectangle, then you need to calculate the area of the rectangle of the foundation, rectangular foundation, and the area of the rectangular, the area of the inner rectangular area in case of its rectangular column or rectangular foundation. We will see that in the upcoming classes, inshallah. Okay. Shear area. Now, how many areas will be cut? There will be 4 areas will be cut. Each one of them is for a dimension of 1.84. And once again, they are similar or they are the same value because we are having a square column and a square foundation. Okay. Now we have got this value, which will give us a shear stress of 0.344 Newton per millimeter square. Okay. So this is whatever I have explained for you, but I have tried to illustrate it more so you can understand rather than only following or memorizing the steps. Okay, so we have got the amount of shear stress caused by the load in case of one-way or in case of a two-way shear. Now the next step is to calculate the concrete shear stress, how much the concrete can take in terms of shear. And we have used this particular formula in the design of a slab. So if we return back to our code, okay, if we return back to our code, to the table of contents, okay, you can see that whenever we are talking about shear reinforcement, we'll have shear stress of the loading. We are going to have VC, which is the shear stress of the, it's not shear reinforcement, it's the shear stress of concrete, which is VC. Now it says for you here, gamma M, we said it's 1.25, and I told you previously that there are 2 places to calculate this 1.25. B is 1000 because we are designing for 1 meter. D is your D average. AS is your area of reinforcement, okay, the maximum area of reinforcement or the provided one. Now, the only thing that you need to take into account are these conditions which have been given here. They say for you AS over BD should not be greater than 300, 400 over D should not be lesser than 1. Okay, so these are the things which are to be taken into account. Plus, if your grade of concrete is more than 25, if you remember I told you, if your grade of concrete is more than 25, then you need to modify this equation. Why? This equation and this table has been made for grade of concrete of 25. If your grade of concrete is stronger than 25, eventually your shear stress will be stronger than this value of BC. How to find the newer value? You will find it by multiplying whatever value you have got from this equation into FCU divided by 25 to the power of 1/3. It's like you are getting a cross multiplication or a ratio between the older one and the newer one. So now we will return and apply whatever values in the equation. You can see that we have substituted gamma m to be 1.25, average AS provided, or AS, let us say not average, but AS provided is 1050 if you are using the table, 1048 if you are using the manual method. And then you can see that this will not exceed 3. It is 0.21. 400 over 480. Now you can see 400 divided by 480 to the power of 1/4 should not be lesser than 1. I have kept it from the beginning to be 1. If it's lesser than 1, it will cause you a problem because you cannot use it. The code says for you it should not be lesser than 1. So we have 1. And then the final value we have got for VC is 0.381 if your grade of concrete is FCU 25. Now my problem says that my grade of concrete is not FCU 25. My grade of concrete is stronger than that. Now, of course, if your grade of concrete is stronger, it means that your shear stress is going to be stronger as well. How to do the modification? We said we can find the newer shear stress of the concrete by multiplying the old or the 25, the grade 25 shear stress into FCU divided by 25 to the power of 1/3. And we have got our value of VC new to be 0.425. Okay, we have got our shear stress to be 0.425. Now the concrete can take up to a shear stress of 0.425. We need to check how much was the loading, shear stresses. Now you can see for one-way shear, we have got it to be 0.37. My loading is going to cause me a shear stress of 0.37. My two-way scenario will cause me a shear stress of 0.344. The concrete can take up to 0.425. Now, do you think that you need to increase? Do you think that you need to increase? Reinforcement? Do you need to increase anything? If your concrete is already strong enough, your concrete is taking, or your concrete can take up to 0.425. The loading is causing you a shear stress of 0.37 and 0.344. Do you need to provide extra reinforcement? Okay. So you will say that the concrete is sufficient. I don't need to include or to add another shear reinforcement. Now, since I have explained it for the other section as well, now normally if you have verified, if you have tried to solve many problems in the design of slabs, you will see that slabs are normally failing in deflection. Okay, slabs are normally failing in deflection. Now, if your slab failed in deflection, what will you do? If you have started the problem, okay, if you have started the problem, you reach to the end, and then it appears for you that your actual span by effective depth is more than the limit, means it fails. What will you do? What will you do? Once again, in case of a deflection for a slab, you have designed everything was safe, you reached to the deflection and it failed in deflection. What will you do? As this maybe is going to come for you in your midterm examination. Yes, any idea?
Write a note that we need to redesign slab.
Redesigning the slab is not a logical answer because you will be spending a lot of time once again to redo it. Right, it will take you a lot of time to redesign it, right? Once again,
Yes.
I
Increase
said,
the depth.
okay, so one solution is to increase the depth, another solution. So for you,
Reinforcement.
okay, so for you as engineers, you should know what are the solutions. Okay, you should know what are the what are the solutions which will stop your failure. Okay, if it failed in this failure, how to make it safe. I'll give you an example, and let us hope that it will be a bit easier for you. Now let us say that I have two books, okay, two books of the secondary school. Let's say, I have two books of the secondary school. Okay, these books are of, let's say, 100 pages each. 100 pages each. I tried to cause bending. Okay, I tried to bend. Okay, because bending is going to cause your deflection. Okay, so I tried to bend. Okay, now both of them are going to have the same bending, right? I have two books which are exactly the same. Each one of them is having 100 pages. I tried to bend with the same amount of bending, with the same force. You will have the same deflection, right? Okay. Now what will happen if I change the scenario? I kept two books in one side and one book in the other side. Which one is going to be harder for you to bend? Which one is going to be harder for you to bend? The two books. Okay, the two books. So now you can see by increasing the depth, you will reduce your deflection. Right? By increasing the depth, you will see that it's going to be harder for you to bend it. It means that it's going to be lesser to deflect. Are we okay? Are we fine about the concept of the depth? Is it clear? Okay. Now the second scenario, I have the same books, exactly the same two books. One is in my right side, one is in the left side, and I try to bend these two, but I have kept two pens inside the first book. Two pens. I kept two pens inside the first book, and I didn't keep anything in the other book. So one book is having two pens inside. Okay, the other one is not having. Or let me give you another scenario. If I have a foam, okay, if I have a foam, and then I kept two stick inside, two barbecue stick, one foam, fillet, and then I kept two barbecue stick inside, and then I have the other foam, but without any barbecue sticks. Which one is going to be harder for you to bend? They are having the same depth. The book with the pen, the foam with the barbecue sticks, or the plain book and the plain foam. Okay, you will see the one which is having reinforcement is going to be harder for you to bend or harder for you to cause deflection for. Now, what if I have two foams? One foam is having two sticks, another foam is having 10 sticks. Which one is going to be harder for you to to deflect. 10. Now you can see now, in one scenario, by increasing the depth, we have controlled the deflection. In the other scenario, by increasing or playing the reinforcement, you can see that you have caused your deflection to reduce. Okay. The good engineer is the person who will know, if this failed, then what shall I do? Okay. If you know the keys of the doors, it will be very easy for you to open the doors rather than breaking the door. Okay. Now returning back to our problem, if it fails in shear, if your foundation, the main failure in foundation is normally shear, because it will not deflect. If it failed in shear, it came in your midterm examination, and your foundation has failed in shear, what will you do?
Increase the depth.
Okay. So we can say that by increasing the depth, okay, we are going to resist, or we are going to stop somehow the shear, okay, or reduce the effect of shear. The same example of the foam, or the same example of the books. If I kept 2 books in one side, I tried to cut them with a knife, and then in the other side I have 10 books. So 2 in one side, 10 in the other side, and I try to cut these books. Which one is going to be harder for me to have shear, or to cut fully? Which one? The 2 books or the 10 books? Which one is going to be harder for you to cut? 10. So once again, if you increase the depth, it's going to be harder for you to cut. Okay, it is going to be harder for you to cut. The same thing when it comes to reinforcement. If I increase my reinforcement, then once again it's going to be harder for me to cut it. Are we okay? So if your slab fails in deflection, or your foundation fails in shear, you need to use your logic to decide. Okay, and the regular decision is to increase the depth or to increase the reinforcement. Are we okay? Okay.
Mr. Do we increase both, or do we choose depending on the situation?
Why would you choose both? Normally we prefer in when it comes to slabs, we normally prefer to avoid deflection. We normally prefer to increase the depth. Increasing the depth is cheaper than increasing the reinforcement, because my slab is a large area. So if you increase your reinforcement, you will be increasing it for a larger area. The same thing for the foundation. When you increase your reinforcement, you will have to increase it everywhere. Okay, and in that scenario, you will be increasing the reinforcement for a larger area. True, you will be increasing the concrete for a larger area as well in both scenarios, but the concrete is cheaper than steel. So normally the preference goes for increasing the depth. Are we clear?
Yes, thank you, Mr.
Okay. Now I have one thing that I have discussed with the other sections as well. With the other section, sorry. Let us say that I have this foundation. Okay. Or let me draw it in the whiteboard better to have a good space. Okay. Let us say here, I have my foundation. This foundation is 1 meter. Okay. And my D average, this is 0.4. Okay. Or let us say 0.3. 0.3. My D average is like 0.4. My D average is 0.4. Okay. Now, how much is the space here? Can you calculate this for me? If the column is the sensor, how much is A and B? Yes. How much is the value of A and B? Okay. So you have got A and B equals to 0.35 and 0.35. What is the distance required for me for shear? I said one-way shear is going to start after a distance of D average, right? Which is 0.4. So in this scenario, what will you do? This was an examination problem that I used to give, or I have given to the students in one of the semesters, and I didn't explain it for them at that time.
Again, Mr.
You have a foundation which is having 1 meter into 1 meter in length and width. Okay, the size of the column is 0.3. You have the distance from the face of the column to the edge in both directions are 0.35. Your D average is 0.4. Okay, now we said that one-way shear will start after a distance of D, and we said two-way shear is going to start after a distance of 1.5 D. So we are talking about 0.4 and we are talking about 0.6. Now this 0.4 and 0.6 are actually more than the available dimension of B and A. B and A are 0.35. What will you do?
Maybe it's not a square.
What?
Maybe the foundation is not a square, it's a rectangular.
No, it's a square. It's 1 into 1.
Increase the area.
Okay. Any other person? Now see.
Mr. He said the average. It means we have to. It's already divided by 2.
Yeah, D average is 0.4. It's D average already. Yeah, that's what has happened with the students at that time. Okay. Now once again, when it comes to structural design, you try to understand rather than memorizing the things. Now the first thing when it comes to shear, is it a problem or is it an advantage? Would you prefer having less shear or more shear? In terms of loading, I mean.
Less.
Less shear. Okay. Now in this scenario, whatever we have drawn, we said the loading of the column is going to concentrate at a certain 45 direction, right? And we said the distance required is d. Okay, the distance required for me for one-way shear is d. For two-way shear, it's 1.5 d. Now, in this scenario, you will see that if this is my foundation and this is my column, I have 0.35 here. I said from the beginning that one-way shear is going to happen after a distance of d, which is 0.4. So one-way shear is going to happen only after this particular line. That particular line, is it inside the foundation? That particular line, is it inside the foundation? Is there any area to be lifted up? Is there any area after that line to be lifted up from the foundation?
No.
No. So if there is nothing to be lifted up, what is the shear force required to lifting it up? Once again, we said there will be a shear force which is required to lift my portion up. Now you can see that there is a line. After this particular line, the portion is going to be taken up. Now actually this line is outside of my foundation. It means that there is no portion. If there is no portion, it means that there is no force to take it up. It means that your shear force is equal to 0 because your line is outside of your foundation. It means that your shear stress is equal to 0. It means that there is no one-way shear and there is no two-way shear. Are we clear? Are we clear about it? It is
Yes.
a simple thing. One-way shear starts after a distance of d. Now distance of d is 0.4. I have only 0.35. Is it inside the foundation or outside the foundation? If it's inside the foundation, there will be a portion to be taken up. If it's outside the foundation, there will not be any portion to be taken up. If there is no portion to be taken up, of course, there will not be any force. If there is no force, it means that the shear stress is equal to 0. Are we clear? Now, if you say that I'm going to increase my foundation size, you are going to have one-way shear and two-way shear. Now, would you prefer having a problem? Would you prefer bringing the problem of one-way shear and two-way shear for your foundation? No. Okay. Now, the only thing which will cause you a problem in terms of area, is the bearing pressure. You need to make sure that this 1 meter into 1 meter is sufficient to take this particular loading. In terms of shear, as much I make my area smaller, it's going to be better. Okay, the smaller the foundation, the better in terms of shear. Okay, the bigger depth, the better is going to be your shear. Okay, this is going to be exactly something similar as I'm having my paper. Okay, I brought a piece of paper. Okay, I brought a piece of paper, and I have a cup. Okay, a piece of paper, a very small piece of paper. Okay, and I brought a cup, and this cup is taking almost this much of area of the paper. Is it easy for you to cut this particular paper, or is it easier for you to cut this particular paper of A4 where the cup is available here? Which one is easier for you to cut? Case number 1 or case number 2?
2.
Case number 2, why?
More
Because there is
space.
because case number 2 is easier for you to cut the paper, okay, because you have sufficient area. Okay, you can have sufficient area. Now in case number 1, my area is very small. Okay, my area is very small. The effect of shear, the effect of the what you call, the effect of the cup being in the paper goes outside. It requires more area to cut. Okay, so that's why if your shear stress or if your shear line of one-way shear or two-way shear is happening beyond the foundation, it means that there is no shear force. I don't require anything to lift the portion which is outside the foundation. There is nothing existing after the foundation. Okay, that's the scenario that you should know, maybe for your mid examination. The last portion here is going to be the detailing. So now we are going to have 2 reinforcement detailing. One is going to be the X, and the other one, oh sorry, this is going to be the X, this is going to be the Y. Okay, and both of them we said 20 T20. T is the grade, 20 mm is the diameter, at 300 mm center to center. We said this is the reinforcement. This is going to be the hooks. Here in Oman we provide hooks for the foundation, although that in most of the cases these are not required for the design. And these are the starter bars of the columns. Okay, so that's the detailing of your foundation. Any questions? Any questions that you are having? Okay. Any questions that you are having?